everyone, and welcome back to the AI Agent Academy. I'm your host, Sophia.
And I'm your researcher, John. It's great to be back here, Sophia.
Absolutely. In our last episode, we covered the foundational software development skills needed to start building AI agents, namely the cornerstones like version control, back-end development, and APIs.
That's right. Now that we've solidified that foundation, we're ready to move from the how to build the container, to the what of what we put inside it. Today, we're peeling back the layers of large language models, LLMs, to understand how they work.
This sounds like where the real magic happens. So what's the first concept we need to grasp to understand how these LLMs process language?
Today, we're putting two of the most fundamental concepts on the table, tokenization and the context window. They might sound technical, but they are the absolute key to unlocking how an LLM reads, understands, and remembers information.
Got it. So we're talking about breaking down language into pieces that the AI can process. In this episode, we'll be discussing what tokens are, how they differ from words, what a context window means, how it functions as the model's memory, and even how all of this directly impacts performance and cost, right?
That's the plan. This is the next essential step on our AI agent roadmap. Ready to dive into the world of tokens?
I'm ready. Let's get started. How do these massive artificial intelligence models eat text? I mean, when we give them a book, do they read it word by word like we do, or is there some other trick to it?
An excellent place to start, Sophia. That trick you mentioned, that's actually where all the magic begins. Tokenization.
Tokenization. It sounds like arcade tokens or a secret spy code. Unless that's just a fancy term you're using to impress me, is it really that important? After all, we always hear that ChatGPT just predicts the next word.
Oh, it's incredibly important. In fact, that next word prediction is a small but very critical oversimplification. Technically, the models predict the next token. It's a very subtle but vital distinction.
Wait a minute. So words aren't always tokens. My entire linguistic world is being turned upside down right now.
It's not being turned upside down, it's just expanding. Look, for us humans, the smallest unit of language might be letters or words, but for a computer, text is just a long, meaningless string of characters. It doesn't inherently know where a word begins or ends. That's where tokenization comes in. It's the process of breaking down raw text into smaller, manageable units we call tokens.
Got it. So it's like taking the language and chopping it into bite-sized pieces that the digital brain can eat. The art of slicing and dicing.
Exactly. That's precisely it. We call these bite-sized pieces tokens. These tokens can be a single character, like a, or part of a word, like ing in running, a whole word, like cat, or even sometimes a short phrase, like New York. Once the text is broken down into these tokens, each unique token is assigned a unique numerical ID from the model's vocabulary. These numbers are what the LLM actually understands.
That's exactly what I was going to ask. On one hand, you have a massive dictionary, and on the other, spelling everything out letter by letter. There has to be a happy medium. So, John, what exactly are these mysterious tokens? Are they all just miniature words, or are there some shapeshifters in the mix? Are they like linguistic Legos for the LLM?
And absolutely nailed it, Sophia. You've absolutely nailed it. And yes, they're definitely not all the same size and shape. In fact, that's what makes it so interesting. Let me give you a few concrete examples. Let's say we have the sentence, "The immoral cat's name was Martin." The word cat, this would most likely be represented as a single token. The letters themselves don't carry individual meaning. The word immoral, this is where it gets interesting. This word might be split by the tokenizer into two separate tokens, like im and moral. That's because the prefix m is a meaningful subword that changes the word's meaning.
What about punctuation? A sentence like, hello, how are you, would probably become something like, hello, comma, how are you, question mark. The comma and the question mark get their own VIP passes.
Fascinating. So it's a very clever way of breaking things down. But if immoral is 2 tokens and cat is 1, how can we ordinary people predict how many tokens a piece of text we write will have? Is there a secret formula?
Not a secret formula, but there is a general rule of thumb. For English texts, every 100 words corresponds to about 130 to 150 tokens. But this ratio isn't fixed. In languages with longer words, like German or Finnish, the token-to-word ratio can be much higher. In fact, a recent study showed that a Telugu translation produced over 7 times more tokens than the English original, despite having far fewer characters. That's a lot of tokens. So how does this variability and the increase in token count affect the LLM itself? Does it have an impact on its performance or, more importantly, on my wallet?
Laughing. It certainly does, Sophia. The properties of tokens directly impact how an LLM operates. 1, context window management. The context window, which is the LLM's working memory, is measured in tokens, not words. The more efficiently your text is compressed into fewer tokens, the more information the model can remember at once.
2, computational cost. This is a big one. The required processing power increases quadratically with the length of the token sequence. So if you double the number of tokens, the model needs 4 times the processing power. This means slower responses and higher costs. 3, pricing. With cloud-based LLM services, you are almost always billed based on the number of input and output tokens you consume. Since different models use different tokenizers, the same text can result in different costs. This is why efficient tokenization directly translates to saving money.
Wow! So tokens aren't just what the LLM eats, but also how it thinks, how much it remembers, and what it costs us.
Now we are at a perfect crossroads. On one hand, there's the hyper-detailed but expensive method of counting every single letter. On the other, the clunky and inflexible method of swallowing whole words. So one extreme was too hot and the other was too cold. Which porridge is just right for our LLM Goldilocks?
Precisely. And that just right solution is subword tokenization, which enters the scene like a superhero. It's a hybrid approach that aims to combine the best of both worlds.
Hybrid. Got it. So not as big as a word, but not as small as a letter. Does that mean breaking words up somewhere in the middle?
The logic is this. Let's keep very common words like and, cat, go, as a single token. But for rarer or more complex words like tokenization or configurability, let's break them down into frequently recurring, meaningful pieces.
Wait a minute, that reminds me of my Lego analogy. So instead of using a tiny single Lego piece for every letter or a giant pre-built Lego castle for every word, we have a set of common, reusable, standard Lego pieces, like the 2x4, wheels, and windows.
A perfect analogy, Sophia. That's exactly it. And the secret to how we find these standard Lego pieces lies in a clever algorithm called byte pair encoding.
Byte pair encoding? That sounds a bit intimidating. Is it some kind of secret data compression magic?
It's no magic at all. Actually, it's a very intuitive process. Think of it like this. Start from the basics. The algorithm begins by breaking down the text into its most fundamental units, individual characters, or technically bytes. It then scans the entire text and asks, what is the most frequent adjacent pair of characters? Let's say in our text the letters S and H constantly appear next to each other as SH. The algorithm says, I'm tired of seeing S and H separately. Let's merge them and create a brand new single token called SH. 4. Repeat, repeat, repeat. The process doesn't stop there. The algorithm scans the text again, looking for the new most frequent pair. Perhaps the new SH token frequently appears next to IP. The algorithm would then merge those to create a new SHIP token. This find the most frequent pair merge repeat cycle continues until we reach a predetermined vocabulary size, for example, 50,000 tokens.
Wow, so it's like a greedy little algorithm. It's constantly gobbling up the most popular pairs and turning them into bigger, more efficient super tokens. And that's how it learns to break down a word like running into pieces like run and ning, because those pieces appear in many other words.
You've hit the nail on the head. It's not a linguistic process. It's purely statistical and data-driven. It doesn't know the meaning of the word, it just sees which pieces frequently appear together. This is the elegant and pragmatic solution that makes modern LLMs both efficient and powerful.
Fantastic. So after creating these perfect Lego pieces, what do LLMs do with them? And more importantly, how many of them can they keep in mind at once?
An excellent transition. That question leads us directly to the concept of the context window. You can think of it as the LLM's limited workbench or short-term memory. It defines all the information the model can keep in mind at that moment to generate a coherent and relevant response.
Is it like me trying to remember my grocery list? If the list gets too long, I definitely forget the organic cabbage.
It's exactly like that. Think of your conversation as a long back and forth. If all that back and forth fits inside the LLM's memory box, its context window, it remembers everything and gives a relevant answer. But if the conversation gets too long and starts to overflow that box, the model effectively starts to forget the oldest parts. That's when responses can become irrelevant, and those infamous hallucinations can appear.
Hallucinations caused by a limited memory. That's a fascinating image. But you keep saying tokens. So we measure the size of this memory box in tokens, not in words or back and forths.
Spot on, Sofia. That's the key. The size of the context window is measured precisely by the number of tokens. That's why we emphasized how crucial efficient tokenization is. The fewer tokens you can use to express a piece of text, the more meaningful information you can fit into that memory box.
I get it. So why have context windows gotten so large? What was the memory of the first models like? And where are they now? Are they walking around like they've swallowed an encyclopedia?
Enthusiastically. The progress has been truly staggering. The first LLMs had context windows of maybe around 2,000 tokens. That's about 1,500 words or a few pages of text. But now, models like GPT-4 and Claude can handle hundreds of thousands, and Google's new Gemini 1.5 Pro can go up to 1 million tokens.
1 million tokens? That's like holding an entire library in its mind. Besides my brilliant questions, what else fills up that massive memory?
A very good point. That window isn't just filled with your prompts. It often also includes system prompts like, "You are a helpful assistant," that shape the model's behavior. Sourced documents, PDFs, code files, anything you provide to the model as a reference, and information from external tools, especially in RAG systems. This is extra information the model pulls to help answer a query. A few long documents can fill up even the largest window quickly.
Okay then, the bigger the better, right? Let's just max out the memory, the model will remember everything, and it'll be perfect.
If only it were that simple, Sofia. While a larger context window can mean better accuracy, it comes with serious trade-offs. 1. Computational cost. This is the biggest hurdle. The required processing power increases quadratically with the number of tokens. Performance degradation. Surprisingly, LLMs can get lazy in very long contexts. Research shows they perform best when the most relevant information is at the very beginning or end, but they struggle to find important details when they're buried in the middle. It's a real needle in the haystack problem.
Wow, that's a really complex balancing act. So the goal isn't just to make the memory as large as possible, but to find that sweet spot where the model performs best without becoming sluggish, sending costs through the roof, or creating security risks.
Exactly. The context window is where the practical importance of tokenization truly shines. It's not just a technical detail, it's a fundamental engineering and economic decision.
Transition music, curious and mysterious. John, all these tokens, context windows, encodings, what happens when we finally get to the checkout counter? What is the cost of using this AI magic? Is there some kind of token tax here?
Token tax. I love that term, Sophia. And yes, in the clearest sense, there is a token tax. When you use commercial LLM services like Google Gemini, Anthropic Claude, or OpenAI GPT, the fundamental unit of your bill is exactly that, the token.
So we're not paying per word or per character, but directly per token. Does this mean the cost can change between different models?
Exactly. And this is why the topic is so important. Tokens are the currency. Every prompt you send to an LLM is counted as input tokens. Every response the LLM gives you is counted as output tokens, and their prices are often different. Different models, different bills. Each model has its own tokenizer. When you send the same text to one model, it might count as 100 tokens, while on another model, it might be 120. This is directly reflected in your bill.
I see. So every token is essentially a light bulb burning in their service. Are there ways to lighten this token tax and optimize costs?
Of course, there are ways. This is where being a smart developer or user becomes important. 1. Choose the right model. Using the most expensive model for a simple task is like using a cannon to hunt a fly. You can do the same job much cheaper with a less expensive model. 2. Prompt engineering. Keep your commands as short and concise as possible. Unnecessary fluff means unnecessary tokens that directly translate to your wallet. 3. Caching. If your application constantly uses the same system prompt, some services allow you to cache that context. This prevents you from paying for the same tokens every single time. 4. Batch processing. For non-urgent jobs, some services offer batch processing APIs, which can provide discounts up to 50% on a per-token basis.
Fantastic. So it's not just a technology, it's also a game of economics and strategy. The more efficient you are, the less you pay. It's incredible to see how tokenization, that simple technical detail we first discussed, ends up directly affecting our wallets.
Exactly. Tokenization forms both the technical foundation and the economic engine of the LLM world. Understanding it is the key to leveraging this technology in the most efficient and intelligent way possible.
John, at the end of this conversation, I've realized the AI's magic is gone, replaced by a reality that's far more awe-inspiring. I'm no longer looking at a magic box, but at the cleverly designed machine inside it. And I understand that the key is, and always has been, tokenization.
Exactly, Sophia. It's like understanding the digital DNA of language. That knowledge elevates us from being mere users to conscious partners in this technology.
Thank you so much for this illuminating chat, John. And thanks to everyone who tuned in.
The pleasure was all mine, Sophia. Until the next adventure.
Goodbye.